Okay, thank you, Olga, for this introduction. Well, I just joined UrbanT team for 2 years to work on the development of a simulation platform at the urban scale. And in order to present myself, but also to make the link between building physics and urban scale, I will present today this scaling up that it is illustrated through different studies I've been confronted to. The presentation is thus organized as follows. So I will first talk about the building's physics and building envelope. How can building envelope be more than just a separation between two ambiences? I will then, as building need to offer a more comfortable and healthy indoor environment, we need to dig into mass balance as well. So, and ventilation is one of the most important lever arms for both comforts. So how does it work? How can we study it? After that, I will present some experimental results at the whole building scale, so real life with occupants. It is a sort of a big picture of highlighted trends on which applied research is still needed today. And then finally, I will present a very new platform that my last institute just received this summer. I was responsible of the overall energy part, and the platform enabled to consider the building in a more control command field alone, but also in interaction with others. So let's first talk about the building envelope and heat transfer. So I focused on this during my PhD. The idea was to propose something else for the envelope, just a separation between indoor and outdoor environment. So lots of solutions emerged at that time, but only on sensible heat storage and solution were either summer or winter oriented. So in 2004, phase change material was seen as very promising in building applications. So how can PCMs could enhance storage efficiency, and is there a sort of year-round oriented solution? So this question led to a full ventilated envelope, as you can see here, some schema here. So we can be in an open or closed loop configuration, and we can play on the different convection regime within the internal cavity. So you get PCMs on the inner layer, you get a solar panel on the south facades, and you get this kind of lever arms to control the heat storage and the efficient use of energy. So for this, a full test bench has been built with PCMs within sort of cooler box. So it gives you an idea about the research application of this. And it was equipped with around 150 sensors for velocity, mainly air temperature as well, but heat flux meter as well. And with the latter, we just confirmed that playing with the convection regime will enable to configure the heat flux direction. If you are in forced ventilation within the cavity, well, this heat transfer will be greater than this one. And if you're in natural convection, due to the length of the scale length of the inner volume and the internal air cavity, this heat transfer will be greater. Thus, it gives you the ability of playing on the storage and on the direction on which you want to release this energy. So a complete numerical model has been built and integrated in the Transys environment. So it took account for all the thermal transfer processes as well as the melting phase of the phase change materials. The experimental bench was used for calibration purpose, of course, for the model, and mainly for the empirical parameters, which are generally the correlation of convection heat transfers. The model was then used to outline what were the most important parameters, and we used for this ANOVA-based sensitivity analysis. So basically, if you have a model that has a different input that are time dependent, you can do as much as simulation as you want or can, playing on the parameters. Each parameter has a wavelength that is specific to him. Then by making Fourier transform analysis in the frequency domain, you can outline at each time step the most important parameters. So these methods are quite interesting because you can have some time dependent important index, as you can see here, but you need also to be, you also transport some inertia effect, okay? So you need to take caution by interpreting these. Anyway, it gives you a quite nice highlight of important index. So after that, taking the most important parameters, we've made some classical parametric simulation and outlined that playing with convection regime and storage phase change materials could enable to have up to 50% of gains and to avoid the heat waves within the buildings for thermal comfort. So this was a simple example of study, just focusing on heat transfer in the envelope. But as I said previously, indoor ambiences need to be comfortable and healthy as well. So ventilation has a major role in both systems. It has been one of my main research activities the last decade. So ventilation can be naturally driven or forced driven. Let's go into each and through different examples, how can it be studied? So first of all, the displacement ventilation with the buoyancy driven ventilation is largely spread, actually in large building, theater, big halls, and so on. I mean, it's really used as a ventilation process, but it can be also strongly influenced by the envelope heat transfer. So even such experimental approaches can be held at reduced scale for such system. It's still difficult because as we will see later, it needs large water tank and salt water in order to represent the buoyancy flux. So it's sometimes more convenient to use an analytical approach. And besides, experimental approach with salt water does not able to analyze the heat transfers as well through the envelope. So if you take the required balance into one system, for this and for fixed envelope, you have the volume conservation, the mass balance, and the thermal balance, you get this system. And it enables you to highlight how important are the impact of heat transfer through the envelope, so the insulation and the inertia, to the dynamic establishment of displacement ventilation. Here you have an overview of the dynamic establishment of the interface 8. Here, we can highlight 3 characteristic times. The first time it reaches the steady states, but there is always an overshot. So the time when it reaches the overshot, and time 3, the time where you finally reach the steady states. As we can see in these graphs here, so I will not get into the dimensionless parameters that are represented, but it shows you, sorry, my marker is a little bit strange. Well, the continuous line represents the adiabatic condition, and the other line represents the impact of either insulation with heavy or light mass transfer there. So this example aimed to illustrate the coupling of mass balance and thermal balance in the case of buoyancy-driven ventilation. So now for wind-driven ventilation. I mean, it's often mentioned as possible way of making sustainable building because you get rid of a mechanical device that works all the time for maintenance and avoid of maintenance. But mass balance software work pretty well, but the most difficult part in computing the wind-driven potential is to have the good boundary conditions. Because as the main issue relied on pressure coefficients, thanks to wind tunnel, this can be measured at various scale. So here you have the approach on orifice law, which can be easily demonstrated analytically, taking Bernoulli's equation. And in the introduction of a more engineering parameter, which is a discharge coefficient, you take into account the contraction of the flow while it passes through the orifice. And mainly we use empirical coefficient that we fit these parameters on specific orifices that are used in experimental approach. So, okay, these models are not within the urban environment, but they are very useful to fully understand the potential of wind-driven ventilation and the different air paths inside the building. So several kinds of results can be drawn from this experiment. So first of all, what are the minimum velocity wind rows that are required to reach a specific target for a specific configuration of opening? So here we see that depending on the presence or not of a chimney, I mean, the velocity, the wind rows changes drastically as well as the level of the required velocity, wind velocity. Then B, for a specific site and orientation, what can be the satisfaction rate of a specific target? So keeping in mind that the pressure coefficient were obtained in a clear environment, okay? And last but not least, it also enabled to validate mass balance softwares, as we've done with Matisse, which is the reference in France for designing ventilation systems. So how about now coupled? So it's still natural ventilation, but coupled ventilation, buoyancy and wind-driven ventilation. Should it be studied experimentally or numerically? Rigorous scaling laws make it almost impossible keeping air at the main transport, as I said before. So what shall we do? So if we have a look at the required scaling laws just for ventilation, we have the forces ratio, forces ratio to respect are inertia over viscosity, so it's the classical Reynolds number, and buoyancy over inertia force, which is represented often by the Archimedes number. So if you take these forces ratio, you need it imply between two scales to have this local scales relationship. And if you combine these two, you will have this relationship that has to be respected between the two scales. Well, this leads that the temperature increasing should be at a power 3 of the decreasing of the length. Okay, so just for an example, if you reduce by 10 your length size of your experimental model, you will have to increase by 1,000 the temperature, and you will be out of the Boussinesq assumption. So it's difficult keeping air as the main vector transport, okay? But what if partial scaling now? Well, it gives you a way more freedom, but you need to pay caution to the results or the assumptions that you are taking are still valid while making your experiment. Well, this has been done with Decathlon Research Center. A special half-size tent has been built in their lab, and we tuned the heating power to have twice as more difference between outside and the mean height internal temperature. The driving force is the hydrostatic pressure column. So we need to respect this relationship between both scales. Here you have image at the full scale, and here at the half scale. Here you have the results. So we, of course, made temperature measurement in order to tune the heat power, but we measured the air change rate with classic gaze techniques. And what we saw is that keeping buoyancy as dominant, the partial similarity worked pretty well. So this was interesting to check. And after this experiment, mainly all of the tents from Decathlon were tested here for thermal control. And here you have an idea of the measurement facility that has to be, that we put it in each tent. So we get pyrgeometer for long wave radiation, pyranometers for short wave radiation, of course, dry and humid globe temperature, and globe, black globe in order to have the radiation temperatures as well. So how about now mechanically ventilated building? Does it perform better? And does it perform well in every case? Is it resilient? So this is another aspect of my research activity. So for residential application, the design stage has always taken into account the improvement of building energy targets. And they kept a sort of threshold for internal air quality. But keeping saying this, it sounds good, but we forgot by making this, action, we forgot the resilience. It means that we have forgotten that enhancing the building envelope and air tightness has led to strongly increase the sensitivity to the system, to leakage distribution, for example. So here you have a network, classical network for a ventilation system on simple extracting point. And I tried to represent, so keeping a global leakage value, which is measured actually in France for standard requirement. I just randomly distributed the leakage around the envelope. And as you can see from these graphs, 50% of the buildings, randomly distributed leakage doesn't match the thresholds of internal air quality. So this, to me, showed the poor resilience of such system, as one of the main parameters that you cannot control in building is the leakage distribution. I mean. So research activity are needed then and are undertaken through several points. So still ANOVA based here, and you can see that these parameters, well, it was when you take the weather file, it corresponds to a high velocity on the specific direction. So wind velocity has an important aspect, but only on this. only during this period. And of course, you can make plenty of simulation with optimization control on different cost functions in order to draw the Pareto border here and then to make your choice. So this is still ongoing research on ventilation. So now let's make a step forward to a larger scale. Building physics is important, but as shown previously, different elements are combined. And what about real life with real building, real stakeholders from the design stage up to the occupant impact? So it was the purpose of Cometpo's project. It consists in following 20 dwellings from the design stage up to 2 years of occupancy and monitoring indoor ambiences and energy consumption for these 2 years. Partners were asked to propose whatever they wanted, but had to comply with the current standard, RT 2012 in France. And all the solutions should be, almost, available in the market as responsibility were engaged from the builders as well as from the manufacturers. Those houses were bought by real people, okay? So even so, we had some exotic solution with thermoelectricity generator or local urban wind turbines. Most of them were quite classical with heat pump for the domestic hot water and either heat pump or electric heater for the heating. But all had solar panels, as the scope was to highlight if making year-round positive energy building was feasible regarding today's standard. Okay, so here you got some example of what we had. So it's pretty classical house. Each occupant had a full app with all the sensors through plan view of their living spaces or systems. So it was based on volunteering. So the occupants were either energy concerned or applications geek. And here are the main trends from now, because the project is still going on, as some sites have less than 1 year of monitoring. So 1 and 2, heating demand, heating is still the first item of consumption. It's twice as higher than domestic hot water production. And cooling potential from outside is not used for summer comfort. As you can see here from one side, in blue, you have the external temperature, and in orange and red, you have internal temperature from the living space and one bedroom. You can see the people that are trying to open windows here because they're struggling with heat waves, but with quite mitigate effect due to still heat is stored within the mass of the houses. So saying this, I mean, we have research activity to do in order to take profit of this cooling potential that is represented by the outdoor environment. So, okay. And so we still, okay. And then also the lack of expertise in ventilation. Here you have some heat map graphs. It represents the numbers of days on the x-axis and the hours in each day on the y-axis. So it gives you a map, and the color represents the concentration of carbon dioxide in the main room. Okay, so it enables to see the patterns of repeatability each day. So it's kind of an interesting way to plot things, I guess. And what we can see from this graph, so here you have, in the main bedroom with the balanced ventilation system. And here it's extracting only ventilation system. Okay, so it's two different houses, but still the main bedroom. What we can see from this, even that this balanced system could show a higher internal air quality compared to this one, it still go up to 2,000 almost every day. So 2,000 ppms almost every day. Even that CO2 carbon dioxide is not indicator of illness. It is an indicator of the renewable air change rate within the house, okay? So it's quite a good tracer for this. So, I mean, all the house weren't showing such concentration, but several. So, I mean, a lot of new house could present the same trends than these ones. And so the design process might be much too energy oriented rather than resilient, as explained previously. So it passes threshold in deterministic scenario, but real life implies some parameters that are just not controllable. I mean, leakage for sure, but not only. Also the lack of expertise of different stakeholders and their action on other fields than their own field. I mean, in this house here, we found that the duct of the ventilation was smashed by insulation. And even though we tried to move it, it's not efficient. It has to be taken into account from the beginning. So another trend, important trend, this represents solar panels coupled with storage equipment to increase the self-consumption and self-production. So here are some results from a site that have a lithium battery coupled to solar panels thanks to one inverter that also make the energy management for the storage. You can see on the right here the power, production in the same way of in the same presentation padding than before. So you can see the winter time and the summertime here. It's a little bit more than a year of simulation, of measurement, sorry. And here underneath is the state of charge of the battery, the associated battery. I mean, what is important to see that the battery gets full quite early in the morning, then it's stored, the stored energy cannot be used until the production has ended. Okay, so, and and besides, the domestic hot water is not coupled to it. So it is based on low-cost hour schedule. From this, we just made a little study, calibrating a very simple node, one node model, so just energy balance, and try to visualize what would be the benefit of unlocking the battery. So being able to charge and discharge the battery several times a day, and also to couple the domestic hot water as a possible load, letting the low-cost driving otherwise. As shown from the self-consumption and the self-consumption, quite important improvement could be expected. So of course, it is simulation, and a step, sometimes large, but not always, is needed to be marketable. But it also relies on the openness of industry to enable coupling with several devices. So this also questioning us on collaboration between buildings, to my opinion. In this example, the battery is too large for winter condition and it's too small for summer. Large amount of the production is not valued for the owner. So besides, the injected power acts more like a perturbation rather than opportunity for the grid. So from there, we should work on more collaborative exchanges between neighbors at the district level. Electrochemistry storage might be not needed if at all, or could be collectively amortized depending on the ambition. So aside from legal regulation that would be for sure needed in such context, research on energy management strategy are still needed to ensure a really efficient use of this energy. So this gives me the transition to my last point on the building with its environment. What could be the next generation of buildings? Should it be permanently self-sufficient or integrated as an actor at a higher level? Research can be realized separately only with numerical models, but you will still be missing the global vision of unpredictable element of either weather, equipment default, or just occupant. So the last project I wanted to show you is oriented toward this last element. So it consists in a building of 400 square meters for office, collective workshop and showrooms. It is equipped with self-sufficient 24 hours per day to be self-efficient. Well, at least from our pre-designed simulation, this is what the power and capacities of the storage element that we monitored, and of course being feasible in a budget. Even so, it's about 1.5 million euros of investment for such equipment here. All elements taken from available market. So from the technology readiness level, it's number 9. Okay, so this was important also for us for the platform, and the platform aims to enable to develop control and make more robust different approach of energy management strategies. Okay, so starting from the simple if-then-else case with fixed limits, more complicated cases with movable limits every weeks, months, trimester, up to MPCs approaches will also be benchmarked on such site. So taking into account the occupant imply to integrate, first of all, energy feedback to him, and to make the booking process of either rooms, workshops, showrooms, or cars in regards to the energy availability as recommendation. I mean, maybe tomorrow energy management system will just propose the user to move his meeting or to delay it, to postpone it in the next day because of the energy availability that we know for tomorrow and that we guess for tomorrow with some uncertainty. So these axes are currently being developed and applied to such an environment This institute is situated in Toulouse, in CEA of Toulouse. And this, what's next now? So now it's an urban scale. The development of ICT imply such opportunity, imply a big opportunity for this scale, but it also requires important effort to work on the reliability of this data. I mean, it does not mean that because you have ICT development that urban scale modeling will be easier. And the research topic of what level, up to what level shall we consider the different buildings, for which available inputs, of course, for which range of probability for the occupants, usage loads, temperature set points. I mean, we will never have these details for modeling purpose at the urban scale. And the main question then is for which result uncertainty. So thank you for your attention. I guess I respected the time lag that you gave me. And if you have any questions.